All right, so we're going to now start to talk through these robustness facts that I mentioned. And the first one is easy, and the second one is kind of going to be very annoying for both you and me to go through. But luckily, the first one is necessary, so let's ignore the hell that's coming and just deal with this nice thing. Staying still is unnecessary. So we have a cursor right now that's allowed to move in one of three directions. You know, it can either move left one cell, move right one cell, or stay still. And what I want to show is that staying still is unnecessary. This is a tiny, tiny baby fact, um, but it does help in proving the other robustness facts because it will be simpler to think about Turing machines that only move in two directions to deal with less cases, essentially. So, how do we do that? Um, well, let's think about what we want. So let me go ahead and write down, oops, upside down pen. So here's the fact. I'll just say it rigorously. So what exactly do we want? So for any Turing machine M, uh, there is another Turing machine. So remember, in our standard definition of a Turing machine, we're allowed to move in three directions. So this fact is going to be framed with that bias in mind. So this Turing machine can move in three dimensions. What I want to prove is that there's a special Turing machine that effectively never leaves its cursor staying still, that does the same task. So there exists a Turing machine M prime with transition function delta prime such that the third coordinate, remember the third coordinate of the transition function is always the direction of delta prime of sigma q um, is never non-zero, but otherwise m and m prime um, uh, compute all the same functions and halt in all the same decisions. Um, compute all of the same outputs and decide all the same things. So if m halts in a yes state, then m prime will also halt in a yes state. If m outputs like m of x for some x, then m prime of x will also output the same x. If m of x never halts, then you know m prime of x also never halts. So they just do the exact same things. It's just that they're designed differently, such that m prime never has like a stay still result. So that's what we're going to prove. And so let's see how to do that. It's not really hard to do. It's just kind of a little. Think of this as like a warm up exercise. So here's the proof. Um, let's just draw some tape and kind of think about what we want. So let's say I'm staring at the symbol sigma. I'm in state Q, and I'm going to put some other symbol lambda here. So this is my tape. I only really care about two tape cells. Um, and what would a stay still option look like? Well, in general, let's say m, by the way, equals, sigma q delta. So the transition function for m is delta. The transition function for m prime is delta prime. So what delta does, let's say, is this, is that it stays still, so the cursor stays here, but it does put like a different symbol here. Let's call it like sigma prime, and it goes into a new state q prime, but the cursor doesn't move, and so lambda is still right here. So this is what we want to simulate. We want to basically make m prime do the same thing in maybe more steps, maybe not. We'll see. Spoiler alert, more. So what does this actually look like as a transition function? Um, this is the result of delta of sigma q equaling sigma prime q prime 0, right? That's what this does. It sees the symbol sigma in the state q, and it doesn't move, but it redraws the symbol sigma here and goes into state q prime. So what we want is to do this in maybe more than one step. So have for m prime an extra state p, um, and let delta um, prime. So I'm going to define what delta does in this situation. So delta in looking at sigma in state q is going to, uh, let's have it actually change the symbol. We'll go ahead and do that. But now we'll go into this new state p instead of q prime. And we have to move right because, again, we're not allowed to stay still. That's the constraint. Um, and then what's going to happen is that will produce this. Ugh. So now I'm like that. And now I want to jump back, obviously. So I'm going to go ahead and let delta prime of lambda p equal, leave it alone, lambda p -1 uh, for all symbols lambda. So, no matter what's here, it's going to ignore it and jump back. Oh, wait, sorry. It doesn't go into state p, it goes into state q prime. And in fact, I should probably mention that we have a new state p for every q, for every state q. Because I mean, any state could have a staying still option. So basically, we need a unique p state. So if I have 5 states in my Turing machine M, then I'm going to need 5 more states that are p states that basically just do the thing where they jump back. So they just add one extra step to all of the stay still options. But then, so basically, where I would stay still, I instead go into this new state P, jump right, and then go into a new state, and then go back and go from that into the state that I want and jump left. Um, but really, yeah, you need a new P for every one of these Q primes. So if I was going to go into state Q prime, then I would need a P for that Q prime that says basically this is the jump back, but associated with a Q prime, effectively. So I still need a copy of every state, but it's really for the output state and not for the input state. That doesn't change anything though. But that's the idea. That's it. So basically, instead of one step, I have two. Instead of one step of not of staying still, I instead add like 2 more steps where I jump forward and backward for no reason and don't do anything. So so basically, I'm back to this. So instead of going straight from here to here, I go from here to here to here. But I've accomplished the same thing. As you can see, the tape configuration at the end is still the same. That's it. Let's think about time and space. First of all, note no extra space used. Well, I guess if this was a blank symbol, then it would use kind of 1 extra space. So, so at most, well, let me go ahead and say this. Note if M operates in time, f of n space g of n, then our new machine M prime, let's think about what the operating time and space for M prime. Then M prime operates in space at worst g of n plus 1. But as we know, these don't matter, right? G of n plus 1 is still an element of O of g of n. And really, it's the O of g of n that we care about, not g of n itself. So the plus 1 makes no significant difference. Similarly, M prime operates in time at worst. Well, what's the at worst time here? How would you let's think about that. So typically, not all of my commands are going to be stay still, right? They're obviously no, most of them won't be stay still. Staying still is probably the rarity, but we still want to think about like the worst case. So in the worst case, we stay still every single step. Maybe I should write that down. So um, at worst, um, worst case, M stays still each step, resulting in 2 extra steps per step, right? So we basically added on, well, is it 1 extra step or 2? 1 step, 1, 2. Yeah, I guess 1 extra step, but that results in double the steps, resulting in double the steps. So M prime operates in time at worst. Wait, sorry. Um, at worst, 2f of n. Right? If I stay still every step, then I'm going to have one more step for every step, and that gives me twice the number of steps. But again, just like plus 1 doesn't really matter here, 2f of n is still O of f of n. So this new algorithm produces no meaningful results, meaningful differences in time and space. So let me write that down as a corollary. So corollary, by the way, means immediate result of the previous fact. So if you've proven something, then oftentimes a whole flood of things follow from that proof immediately, and those things are called corollaries. So corollary is R, the set of all computable functions, time f of n, and space f of n are always the same class, the same set, regardless of whether or not our Turing machines stay still. So we don't have to worry about that.